One of the most clever ways that we can look at energy, a way to make it a little bit more clear, is by looking at energy curves, energy graphs, sometimes called potential wells, right? These things look like little wells. And so they help us kind of understand the motion of objects. But before we get there, I want to look at this misconception question number 4. And the question is, a ball is thrown straight up. At what point does the ball have the most energy? A, at the highest point of its path. B, when it is first thrown. C, when the ball is halfway to the highest point of its path. Or D, everywhere. The energy of the ball is the same at all of these points. And the problem says, ignore air resistance. Okay, well, the whole chapter is about conservation of energy. So if we're ignoring air resistance, obviously the answer has to be D, right? The energy is going to be the same everywhere. But we also just dealt with problems where we do have non-conservative forces like air resistance and friction, right? If we don't ignore air resistance, which one is the right answer? And this could be even a little bit more rich of a question. What do you think? If you don't ignore air resistance, where does the ball have the most energy? The answer would have to be when it is first thrown. Because if you're dealing with air resistance, the second after you throw it, all your energy, as we saw in the last problem, starts to be converted into work, right? Work done by drag force, and the ball itself is losing its energy, okay? Until it actually at some point will just come to rest. All right, so 2 different answers based on whether you ignore air resistance or whether you accept that air resistance is a real thing, okay? But just FYI, most of the tests you take from this point on and most of what you'll see on the MCAT will ask you to ignore air resistance. Okay, so the next question says conservation of energy and energy curves, right? So we have this energy curve, and we're assuming that this is some conservative force, so that the sum total of the energy of the object at any point along this curve is equal. Is equal, never changes, right? And remember I told you that sometimes potential energy is given with a U instead of PE. That's how we're marking this axis here. So this is all potential energy over here, and this is position. So this is x of m. This is where the object is located, okay? And this is your potential energy. All right? So all this is saying that is that if I have some kind of object, let's say just a ball, right? And I move it in space, it's going to have different amounts of potential energy at different points, right? This could be as literal as actually hills in a landscape, right? Like, if you have a ball that's at the top of a hill, it's going to have more potential energy, and if it rolls down the hill into this point here, it's going to have more kinetic energy, less potential energy, right? It'll, if it has enough energy, it'll roll over another hill, right? These curves could also be like the potential energy of extension, x, if you're pulling on a slingshot, right? So just as an aside here, right, if x is how far you're stretching it, right, the potential energy would be swooping up and increase, right? So these are just graphs that represent if you have an object at a certain position, what potential energy does it have, okay? And so because this is a conservative force, we know that the total mechanical energy, right, must be constant no matter where you are on this curve. So the total mechanical energy, in other words, the potential plus kinetic energy, must be constant everywhere, okay? And this problem is telling us that we're releasing the ball at B, at UB here, right? And it says that UB, the potential energy here at this position, UB, is 12 joules. So the potential energy equals 12 joules, right? And it says that it's released, it's like given a little push, with a kinetic energy of 4 joules. Okay? So that means that the total mechanical energy that our ball starts out with must be what? 16, right? if ME is the total of the potential energy and kinetic energy of the ball at this position, right? And that means that the total mechanical energy there must be 16 joules, okay? And that's going to be a constant no matter where this ball rolls to in this entire path. It's the sum of the potential and kinetic energies is going to have to be 16. That's what conservation of energy means, and that's why it's so powerful, and that's why it lets us predict so much, okay? So let's make a prediction. Part A says, what would be the speed of the particle at, say, 3.5? So that's right here, right? So the ball is rolling down, cruises down to get over here, right? And it wants to know what the speed's going to be right here. Well, how do we solve any conservation of energy problem? You know it by this point. We just say that E1 equals E2. And remember, this is our 1 right over here, and this is our 2 right over here. Okay? They're two different positions. Now, what kind of energy does it have right here? Well, it has potential and kinetic, right? It has 12 joules of potential energy, 4 joules of kinetic energy. But we can just go ahead and add that and just say 16 joules. It starts out with 16 joules, okay? And then what kind of energy does the object have right here? Well, again, it has potential energy of UA plus whatever kinetic energy it acquired by rolling down this energy hill, okay? So we know from the problem that UA is 9, right? So I can say 16 equals 9 plus KE, right? And if I subtract the 9 to the other side, I get 7, right? So if my kinetic energy is 7 joules, right, and I know that that's 1/2 mv squared, right, I just want to solve for V. Now the problem tells me that it's a 0.2 kilogram ball. So this guy over here is M equals 0.2 kilograms. I just put in that mass right over here, right? I multiply by my 2, I take a square root, and I get 8.4 meters per second. That's the speed of the ball as it rolls down this hill, down into this little valley right here, okay? Okay. Second question. The second question says, what would be the speed of the ball down here at 6.5 meters? So here, now we're talking about here. So the ball gets over here. So our new 2 is over here, okay? Well, what do we know about that position? We do the exact same thing, okay? We do the exact same thing. We know we start out with 16 joules over here, right? But the second step is to ask ourselves, what kind of energy do we have down here? Now, there's no more height, right? This is H equals 0. The potential energy is 0 here, right? So that means that if there's no potential energy, this all must have got converted into kinetic energy, right? So now it's simply going to be 16 equals 1/2 mv squared, okay? Again, my mass is 0.2 kilograms. I multiply by 2, take a square root, and I get a velocity of, in this case, 12.6 meters per second. Does that make sense? Well, it's higher than our last answer, right? Which we want it to be, right? This guy has a higher potential energy, so if we're bringing this ball down to this lower position, that potential energy must convert into more kinetic energy, which means more velocity. So it makes sense that we should have a higher velocity, okay? This is pretty cool. It makes something that seems kind of complicated, predicting what the speed is and the energies of the ball at these different locations, right? It makes it so that we can easily predict it because we know the total energy must be whatever it started out with because of conservation of energy. And that total energy was 16 joules. So we can take that 16 joules and set it equal to the potential and kinetic energy at any spot and solve for the velocity. One last little fun question is, can the ball ever be here? Right? And the question is, can the energy that the ball has here ever be greater than the energy it has here, right? Because the ball could never roll all the way to the top, right? Unless the energy it started with is at least as big as the energy at this height. Well, this height is UD, okay? That's 24 joules. How many joules did our ball start with? Well, he started with 16 joules, right? So could he ever get to this high pinnacle? Absolutely not, right? It would be impossible for this ball to suddenly get extra energy unless rockets were attached to the back of it or someone swiped it up or hit it with a bat, right? There's no way that he could get all the way up to the top of this hill if he only started with 16 joules. And this hill is 24 joules, okay? I hope that makes sense. If you have any questions, feel free to reach out.